In our last related rates question, we are going to look at a snowball melting in the sun. So we've got a spherical snowball. We put it out in the sun to die, and it melts it in such a way that the instant at which its radius is 20 centimeters, its radius is decreasing at 3 centimeters per minute. We want to know at what rate is the volume of the ball of snow changing at that instant. So let's draw a picture. So we've got a sphere, so it's a 3D circle. The way we can indicate that a circle that we draw as 3D is we can kind of show that it comes out of the page and also goes back out of the page. So you can just draw in this like diameter here, or this circumference. And this snowball is melting, so it's getting smaller. But one thing that we do have to measure the size of a sphere is the radius, which is the distance from the center, the 3D center, out to any point on the edge of the sphere. So you can think of this as like a ball, and the center is in the middle, like the center of it, right? Or like an atom. And in the nucleus, I don't know enough to, I'm assuming the nucleus is like in the middle, but I don't actually know. I'll just stop talking about, it's a snowball. Okay, so the things that we're talking about here, we have, well, the things we have are radius. We have a radius decreasing because it's melting. We also have the quantity of talking about volume. And that's really it. So we need something that relates volume of a sphere and radius of a sphere. And if you look back at the front page of the related rates questions with our geometric formulas, we do know that the volume of a sphere is 4/3 pi r cubed. Okay, so let's make a column of things that we know, or the things that are given, and then also a column of things that we want. Okay, so we know that the sun melts it in such a way, okay, the volume is decreasing. The instant at which its radius is 20 centimeters, its radius is decreasing at 3 centimeters per minute. Okay, so the radius decreasing, that's the change in the radius. So that will be represented as dr dt. Because the radius is getting smaller, we need to interpret that decreasing mathematically as a negative. So this will be negative 3 centimeters per minute when r is 20 centimeters. They're kind of tied together. So that's from the second sentence. In the third sentence, it says at what rate is the volume changing? So we want dv dt at that instant in time. So in other words, when r is 20 and dr dt is negative 3. Okay, so I think that's all the information we can take from these few sentences here. So, our equation is v equals 4/3 pi r cubed. The volume is not constant over time. It's changing as the snowball melts. The radius is the other variable that is also changing over time. So we can't plug anything in before we differentiate. So I think it's time to differentiate. Right, and this is implicitly, of course, with respect to time. So the derivative of v will be dv dt. The 4/3 pi is, that's just a big fancy constant. So it will be multiplied by the derivative of r cubed, which will be 3r squared. But we differentiated a variable here. We differentiated r, so that needs times dr dt. Then we can simplify this. The 3 divided by 3, that cancels out. So we just get 4 pi r squared times dr dt. All right, so now we want to plug in the things that we know and find the thing that we want to find. Okay, so we don't know dv dt, that's what we're looking for. We want dv dt when the radius is 20, and we know dr dt is negative 3. So we'll square 20, we will multiply that by 4, then we will multiply that by 3. Um, and this comes out to be, let's see, 4,800. So, and the pi will still be there. So dv dt will be negative 4,800 times pi. Now the units of this volume is a cubic measure because it's 3D. So if radius is in centimeters, when you cube radius, you'll get centimeters cubed. And then the time is in minutes. So that'll be cubic centimeters per minute. This is a huge snowball, I think. That started off really large. It's losing a lot of volume every minute, but that's what the math says, so that's what we'll go with. All right, so this is our last related rates question. You know, every single one of them is different somehow. I think that you have all the tools that you'll need to, you know, go about solving these problems in other situations. Keep being persistent. Try them again if you get them wrong, and just kind of, you know, go back and see if there are some things that you're missing. And come to office hours if you want to talk about any of them. All right, have a great day. Have fun. Do some math, and I'll see you later.